Okay, good day. This is Honors Algebra 2. I am Mr. McCulley, and this is the video presentation for section 4-4 on complex numbers. Let's get to the learning goals. The learning goals are we're going to perform some operations with pure imaginary numbers, and then we're also going to perform operations with some complex numbers. So before we get to that, let's do a little quick review of reducing radicals. So the first 13 perfect square roots are these. They are 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, and 169. Now, if you don't have those in your long-term memory, I suggest you take some time to get them into your long-term memory because you will be reducing lots of radicals here from here on out, and it's good to at least know these first 13 so that you can make some of your work a little bit easier. So a couple of properties of exponents that we can use to simplify our radicals is, for instance, if you have the square root of the product of two values, you can make that equal to the product of the two square roots. And in this particular instance, if you take the square root of a fraction, you can split that up into a fraction of the two square roots. And we use that for reducing our radicals. Now you'll notice that 18 is not in this list of perfect square roots, but it does have a factor that is. 9 is a factor of 18. So I can rewrite this expression as the square root of 9 times 2. That gives me the 18. This first property of exponents says that this is now the square root of 9 times the square root of 2, which I can rewrite as 3 square root of 2. Now I should check. I cannot reduce 2 because, again, 2 is not a perfect square root. It is the result of the square root of 4, but it is not one of these values that are under the radicals. All right. Rationalize the denominator. You should not leave a radical in your denominator. So the way that we're going to do that is we're going to use that second property, this property right here, and we're going to go the square root of 9 over the square root of 2. And then we're going to multiply by a funky 1. This is a McCulley term. I made this up myself just so that I can remember it. And we are multiplying by 1. We know that when you go a times 1, you get a. So if I multiply this by 1, I will get that same value. I'm not changing it. In this case, the funky 1 is going to be the value of the denominator over itself. And so what we're going to do is we're going to multiply the square root of 9 over the square root of 2 times the square root of 2 over the square root of 2. Now I'm going to simplify a little bit here first. Remember, the square root of 9 is equal to 3. So on the top, I will have 3 square root of 2. And the square root of 2 times the square root of 2 is the square root of 4. And we can take the square root of 4. That's just 2. So 3 square root of 2 all over 2 is going to be my final answer. Remember, when you're solving an equation, if you must take the square root or even root of both sides of the equation, you must consider both the positive and negative solutions. So from the last one, if we were to solve this by extracting square roots, I go x squared is equal to 9. So I'm going to add 9. Here I'm going to take the square root of both sides. And I need to remember to add plus or minus. So I've got x equals plus or minus the square root of 9, x equals to plus or minus 3. An intuitive look at imaginary numbers. Now we know that the square root of 9 is equal to 3 because 3 times 3 has to equal 9. That's how we know it. But if I try to use similar logic on the square root of -9, I have some issues because let's say, for instance, it's just a. By the same logic, a times a would have to equal -9. Now there's a problem with that. If a is positive, then a times a is going to yield a positive. If a is negative, then a times a will still yield a positive. So we have a little bit of a dilemma. There is no real number a that makes the square root of -9 equal to a. There just isn't. We came up with the imaginary unit. And that imaginary unit is the square root of -1 is equal to I. I will usually write it I like that. If I is the square root of -1, then I squared would be the square root of -1 squared. And we know that square and square root cancel out, so I'll get -1. I to the third is the same as I times I squared. Now from this one above, we already know what I squared is. We know that it's -1. -1 times I is going to be just -I. And then I to the fourth. Well, I to the fourth can be broken down to I squared times I squared. And we know that I squared is equal to -1. So I have -1 times -1. That'll give me +1. So here's the deal. Whenever you multiply through by negative, or whenever you multiply, so here's the deal. When you multiply through by I, so here's the deal. When you multiply I by itself, every multiple of 4 times, you're going to get 1 back out. So I to the 8th is going to be equal to 1. I to the 12th will be equal to 1 because this is I to the 4th times I to the 4th, which would be 1 times 1. And this one would be I to the 4th times I to the 4th times I to the 4th to get my 12. That would be 1 times 1 times 1. All right. So if I wanted to do something that was even bigger than that, let's say I to the 57. Now, 4 doesn't divide 57 evenly, and I get that. But if I go 57 divided by 4, I'll get a 1. We'll put a 4 there. I get a 1. I get a 7. I get 4 there, and I get 16. I get 1 left over. So in this case, I will have 4 sets of 4, which will all be 1s. So this is I to the 56 times I to the 1st. That gives me my 57. And we know that I to the 56th is going to be 1, because that's multiplying by itself a multiple of 4 times, times just I, that'll give me I. So I to the 57th is just I. So when you're dealing with radicals that have negatives in them, you must always factor out the imaginary first. So you'll notice here I have an example. Simplify the square root of -8 times the square root of -4. The first thing that you should do is bring that negative out and change it to an I. And so if you can see this step, you can just skip it. If you can see the negative out, you can rewrite it. You don't have to do this middle step. You can just go I square root of +8 and I square root of +4. Now we can rewrite in any order. I times I is I squared. The square root of 8 is going to reduced down to 2 square root of 2, and the square root of 4 is 2, and then we can reorder, remembering that I squared is equal to negative 1. 2 times 2 we can reorder, times the square root of 2. I'll have negative 1 times 2 is negative 2 times 2 is negative 4. I cannot combine with this square root of 2, so that is going to be my final answer. Complex numbers. A complex number consists of a real part and an imaginary part in the form a plus bi, where the a is the real part and the bi is the imaginary part. So an example of a complex number is going to be 2 plus 3i. If b is equal to 0, then we call the number a pure real number. If a is equal to 0, we call the number a pure imaginary number. As for an example, if just 3 by itself is a pure real number, and 4i is a pure imaginary number. Complex conjugates. If a plus bi is an imaginary number, then a minus bi is its complex conjugate. As an example, if we have negative 4 minus 3i, its complex conjugate is negative 4 plus 3i. So when you find the conjugate, all you're changing is the sign in between. You do not change the sign of the real part. The product of a complex number and its conjugate is always a real number. And again, we talked about that a plus b times a minus b equaling to a squared minus b squared in the last section. It's coming back for us to use with complex conjugates, because when we multiply complex conjugates, the results are real numbers. That means they have no imaginaries in them. Let's do some simplification here. Let's talk about this. Whenever you simplify, you must deal with the negative under the radical first. And we'll make that simple. We'll just go I times the square root of 100. And we're going to simplify square root of 100. And we know that from our list at the beginning of this lesson that 100 is a perfect square. It is 10. And we can say that this is I times 10. Now, technically this is okay, but proper form has the I last. So we'll call this 10i. For this one, we are going to add the real parts and the imaginary parts. In previous lessons, we called that combining like terms. So let's write this out. I'm going to have 12 minus 9. That is my real part. And then to that, I'm going to add 5i minus negative 2i. So I'm adding my real parts and my imaginary parts. 12 minus 9 is going to be 3. 5i minus negative 2i is going to be positive 7i. Simplifying. Here, I want to make this into a complex number. And to do that, I need to remove the imaginary from the denominator. And the way we're going to do that is with a complex conjugate funky 1. Alright, so I've got 2 minus 4i over 2 minus 4i. Now in the top, I just have to distribute. 5 times 2 is 10. 5 times negative 4i is negative 20i. Here I have to distribute, or I can recall a plus b times a minus b equals a squared minus b squared. And so in this case, my a is my 2, so I'll go 2 squared minus, here is my b, 4i squared. And so I got my 10 minus 20i. I can't do anything with that because those are unlike terms. All over 4 minus, well, this will be 16 times negative 1. When I square that, 4 squared is 16, I squared is negative 1. 4 minus negative 16 is the same. 10 minus 20i all over 4 plus 16 is 20. I can take 10 out of each term. Ten divided by 10 is 1. 20 divided by 10 is 2. And then 20 divided by 10 is 2. This is acceptable, or a half minus 1i. Finally, we're going to solve, and since we have just an x squared and not an x in it, the first thing we're going to do is we're going to subtract 50. So I'll have 2x squared equals negative 50. Then we will divide by 2. That'll give me x squared equals to negative 25. And then I have to take the square root. To add plus or minus. And so I've got x equals plus or minus the square root of negative 25. X equals, well, deal with the imaginary first. So I've got plus or minus I square root of 25. And 25 is a perfect square. My final answer is x equals plus or minus 5i. Alright, I know that's a lot. We went fast, but that is all I got for today. So, the Mandalorian fun fact of the day: in the Star Wars timeline, the Mandalorian occurs 5 years after the events in the Return of the Jedi and 25 years before The Force Awakens. So, that's all I got for today, folks. Have a good day. Bye.